In this first video, in a sequence of 4, we will make some statements and pose some questions. We will mostly focus on real numbers, so these are all numbers on the number line or the real line. This is an example of a field. As we'll see, it's more like a jungle. We will look at the composition of real numbers, which begins with the natural numbers, which are the positive whole numbers. We then have the integers. These are 0 together with positive and negative whole numbers. They contain the natural numbers. And then there are the rational numbers, or rationals, or what we might term as fractions. These are all numbers of the form p divided by q, where p and q are integers and q is non-zero. Here are 3 examples. The rational numbers contain the integers which contain the natural numbers. They're all within the set of real numbers. We might ask the question whether there's anything in the grey space shown. So with the natural numbers, the integers and the rationals, we know that each is a subset of the other as shown. But the question is, are all real numbers rational numbers, or are there some real numbers that are not rational? Well, the answer, of course, is yes. These are called irrational numbers or irrationals. They're all real numbers which are not of the form p divided by q, where p and q are integers and q is non-zero. So those are all the numbers in the red space shown, the irrationals. This is the most common of examples, the square root of 2. It doesn't repeat itself, it's not recurring, otherwise it would be rational. The golden ratio is also another example of an irrational number. You can see examples of where the golden ratio appears in folding of paper, in the pentagon shown, the aspect ratio of some famous ancient buildings, and indeed in the design of a credit card. So let us begin by proving by contradiction that the square root of 2 is irrational. Let's suppose the opposite, that the square root of 2 is rational, i.e. it's in the form of p divided by q, where p and q are integers and q is non-zero, and that p and q have no common factors. So any factors they might have had in common have been cancelled. If we square this expression and rearrange, we see that p squared is 2q squared, which tells us that p squared is even, and so p must be even. We can prove that last statement by contradiction too, because if p is odd, then p squared would be odd, and yet p squared is even. So p must be even if p squared is even. So p is of the form 2 times k, and if we square that and set 4k squared to be what p squared is, which is 2q squared, then q squared also becomes 2k squared, so q squared is even, and so q is also even. So both p and q are even. But of course, if p and q are both even, they will have a common factor of 2, which is a contradiction, since we assumed that the square root of 2 was p divided by q. So rational where p and q have no common factors. In other words, we've got a contradiction and we cannot write the square root of 2 in the form of p divided by q for integers p and q. So that concludes our proof by contradiction that the square root of 2 is irrational. Now there are other irrationals, for example the square root of n, for all natural numbers which are not a perfect square. So they're not of the form m squared for some natural number m. So for example the square root of 7 is irrational. Now we will note that if n is not a perfect square, then the square root of n is irrational, but it also happens to be the solution of x squared minus n equals 0. We've already seen that the golden ratio is an irrational number. Although we haven't proved it, you can do so as we did for the square root of 2, or you can use the result above. The sum of a rational number and an irrational number will be an irrational number. Pi is also an irrational number. This was shown in 1761. E, the base of natural logarithms, is also an irrational number. That represents the area under the graph y equal 1 over x between x equal 1 and x equal e being 1. So that was shown to be irrational by Euler in 1737. Now what about the square root of 2 pi and e? Are they only irrational or do they differ in other ways? Well, we know that the square root of 2 satisfies this quadratic equation, and phi, the golden ratio, satisfies this quadratic equation. Now these are polynomial equations with rational coefficients. In this case they all have integer coefficients, but they are also rational coefficients. Any number which is a solution of a polynomial equation with a rational coefficient, including where it has integer coefficients, is called an algebraic number. Note that rational numbers are also algebraic because they are solutions of qx minus p equal 0 if x is that rational number of the form p divided by q. But are all irrationals algebraic? So the square root of 2 is algebraic, the golden ratio is algebraic, both are solutions of polynomial equations with rational coefficients. But what about pi and e, for example? Are they algebraic? Are they solutions of a polynomial equation with rational coefficients? Now we'll denote the set of algebraic numbers shown in green, but they also include the rationals, the integers and the natural numbers. So the algebraic numbers are rationals and the irrationals that we've seen, the square root of 2 and the square root of 5 and so on. But what about pi and e? Are they in the green part or the red part? So there are irrationals that are not algebraic. So they're not solutions of polynomial equations with integer coefficients, and those are called transcendentals. So pi is not a solution of such an equation, so it's not algebraic, it's transcendental. And this was shown in 1882. E is also not algebraic. It's not the solution of a polynomial equation with rational coefficients. And that was shown in 1873. So irrationals that are not algebraic are called transcendental numbers or transcendentals. And pi and e are the most famous examples of transcendental numbers. So we have the composition as shown. The natural numbers sit within the integers, sit within the rationals. All of them sit within algebraic numbers, and there are algebraic numbers which are rational, so just in Q or within that. And there are algebraic numbers which are irrational, which just sit in the green part. For example, the square root of 2. There are also irrationals which are algebraic, like the square root of 2, and irrationals which are not algebraic, like pi and e. So the irrationals straddle both the algebraic numbers and the transcendental numbers. The transcendental numbers are all the ones in the red zone. So what other transcendentals are there? Well, these videos are all about classifying numbers as to whether they are irrational or not. So whether they sit inside or outside Q. But if they are rational, so they're inside Q, they are also algebraic, and they're definitely not transcendental. They're not in the red zone. But if they are irrational, they may be in the green zone and algebraic, like the square root of 2, or they might be transcendental, like pi and e. If they are transcendental, they're in the red zone, and they must be irrational. So pi and e are transcendental, and hence they are irrational, which we have already said. The square root of 2 is algebraic. It's not transcendental, but it's also irrational. What about the square root of e and the square root of pi? Well, they are both transcendental and also hence irrational. What about powers of pi and e for rational R powers? Well, they are transcendental and also irrational. For example, if R is a half, the square root of pi and the square root of e are both transcendental and hence irrational, as are pi squared and e squared, which are powers of pi and e with a rational R, which is 2. What about if we raise a transcendental number to an algebraic power, as opposed to a transcendental number to a rational power? So, for example, if we take the square root of 2 as the transcendental number, or pi as the transcendental number, and raise that to a rational power, well, that is also transcendental and hence irrational. What about if we raise a transcendental number to an irrational power? What about, more generally, a transcendental number to a transcendental power? What about, for example, e, which is transcendental, raised to the power pi, which is also transcendental? Now, there is a famous theorem dating back to 1934, which says that if you have an algebraic number, so a number which is a solution of a polynomial equation with rational coefficients, for example, the square root of 2, the golden ratio, but algebraic numbers also include rational numbers and integers and natural numbers. If you raise an algebraic number of the kind described to a power which is both irrational and algebraic, then that number is definitely transcendental, provided that algebraic base is neither 0 nor 1. So for example, 2 raised to the square root of 2, 2 is algebraic, the square root of 2 is irrational and algebraic, so this number is definitely transcendental and hence also irrational. The square root of 2 raised to the square root of 2 is also transcendental and hence irrational for the same reason. Is it possible, for example, to have an irrational number raised to an irrational power and end up with a rational answer? Well, one easy example is if you have e to the power log 2. E is irrational, log 2 can be shown to be irrational, but e to the log 2 by definition is actually 2, which is rational. But here's another example where the square root of 2 to the power square root of 2 we've seen above is transcendental and hence irrational, and we're raising that to the power of an irrational number, square root of 2, and if you simplify that expression you end up with 2, which is a rational number. So yes, it is possible to raise an irrational number to an irrational power and end up with a rational answer. So the underlined expression in the bracket is definitely irrational because it's transcendental from the theorem above, and the power is also irrational and algebraic. And when we calculate it, we see that the answer is 2. So we know it's rational. So we've just asked the question whether we can have this statement being true, and we've seen that this was the reason. We knew that by the theorem proved in 1934 that the expression in the bracket is transcendental and hence irrational, and the power of that number is also irrational, and the answer was 2 rational. But we don't even need to use that theorem to prove that result. We can prove that as follows. Consider the expression as shown. Then either the number underlined is rational or irrational. Let's suppose that the square root of 2 raised to the square root of 2 is rational. Then this indeed is an irrational number raised to the power of an irrational number. So if the square root of 2 raised to the square root of 2 is rational, we already have an example of an irrational number raised to the power of an irrational number with a rational answer, because that's what we assumed. Even if we don't know the square root of 2 raised to the square root of 2 is rational. If it was, then we have an example. But if it's not rational, then it could be irrational. Okay, if the square root of 2 raised to the square root of 2 is irrational, then we have it raised to the square root of 2 by simplification being a rational number. So you don't actually need to know whether the square root of 2 raised to the square root of 2 is rational or irrational. You can prove that whichever it is, you still end up with a rational answer and an example of the form irrational raised to an irrational being a rational. So it just shows you that even that theorem in the previous slide is not needed, and it's not even necessary to know that that base is rational or irrational to conclude that you have an example of that form. What happens if you add an algebraic number to a transcendental number? Will that be transcendental? For example, the square root of 2 plus pi. Is that transcendental? Is it possible to have a transcendental number added to a transcendental number that isn't transcendental? What about pi plus e? Both are transcendental. is their sum transcendental? We conclude this video with a few further examples and ask the question whether the numbers shown are irrational or rational, and if they are irrational, are they algebraic, or are they not solutions of polynomial equations with irrational coefficients and hence transcendental? Well, the number shown, which is an infinite sum, turns out to be log 2, and that is indeed transcendental and hence irrational. This interesting number, as shown, which is a number with a decimal expansion 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and so on, is also transcendental and hence irrational. This infinite sum with factorials in happens to be E, so it is also transcendental and hence irrational. This number, on the other hand, which is an alternating sum with fractions with denominators which are only odd numbers, happens to be 1/4 of pi, so that's also transcendental and hence irrational. This strange number is also transcendental and irrational. If you expand it much further, it turns out that from the 19th decimal place onwards, there are 183,128 consecutive ones before it changes to 272. This number, with squares of natural numbers on the denominator, is an infinite sum. It's also transcendental and irrational because it's 1/6 of pi squared. This is a similar series, but with alternating signs. That's also transcendental and irrational because it's 1/12 of pi squared. Here we have squares of odd numbers on the denominator. That's also 1/8 of pi squared, and we know pi squared is transcendental, so this is also transcendental and irrational. What about raising the natural numbers to the power 4? Well, that's 1/90 times pi to the 4. That's also transcendental and irrational. And indeed, all series of the form shown where n is greater than or equal to 2 and even will give you a transcendental irrational number as an answer. This number, where every digit is 0 except in the factorial decimal places, as shown, is also transcendental and irrational, as is this number, as is this number, as is this number here with a decimal expansion as shown. So we've seen many examples of real numbers that are within the natural numbers, or within the integers, or within the rationals and the irrationals, and algebraic numbers, which are numbers that are solutions of polynomial equations, which include irrationals like √2, but also rationals and integers and natural numbers. But we've also seen transcendental numbers, pi and e, and many others so far, which are both irrational but are not algebraic, in the red zone, because they're not solutions of polynomial equations with rational coefficients. So as we move to the second video, download and print the PDF document that you see on this page, entitled "I'm a Transcendental, Get Me Out of Here? Questions." Find something to write with, and then watch the next video.